Okay, thanks for coming. So today I'm pleased to have Hidde Koerts from Waterloo. He's a student of Sophie's Buckle, and he'll talk about tournaments. Yeah, please.
Thank you very much. So today I'm going to talk about characterizing large clique number in tournaments, which is some recent work together with Logan Crew, Sinwei Fan, Ben Moore, and Sophie Sparkle. So first of all, what is a tournament? For some of you this might be very rudimentary, but I'll go through all the definitions. So a tournament is an orientation of a complete graph, so a directed graph where between any pair of vertices we have exactly one arc, so one direction. Now, in general structural graph theory, we like coloring things. This is no exception. But what notion of coloring makes sense here? It's not immediately obvious. Every pair of vertices is adjacent. So we use a coloring notion for digraphs, dicoloring, where we partition the vertex set into acyclic sets. So if we look at this example, I have a red-blue coloring of this digraph here. And even though some of the color classes might contain cycles, like the red one, they're not directed. So each color class is acyclic. Now, why is this a natural notion of coloring for digraphs? And that is because if you take any old undirected graph and you color it, and now I replace every edge by a digon, so two anti-parallel arcs, then the notion of coloring in undirected graphs is exactly equal to, or equivalent to this notion of dicoloring. Because any pair of vertices that were adjacent in the original graph are now in a two-cycle together in the digraph, and so they cannot receive the same color. And then just like any other coloring notion, we care about the minimum number of colors needed, and so the dichromatic number denoted by vector chi of d is the minimum number of colors needed for any dicoloring. So this concept of dicoloring and the dichromatic number was first introduced in the 80s by Neumann Lara, but has really picked up interest in the last 10 to 15 years. There's been a lot more focus on this notion, especially when it comes to also looking at induced subgraphs. Okay, but what about tournaments? So some tournaments, really counterintuitively, even though they have all possible pairs of vertices are adjacent, some of them are still one colorable. If we take a transit tournament, so we fix some ordering of the vertex set, and all the edges, all the arcs go one way, so forward in this ordering, then it's one colorable because there's no single directed cycle in this entire tournament. But is this the case in general? Can we always one color tournaments? No, obviously not. If we take a directed triangle, this is a tournament, and it requires at least two colors because it is a cycle. Directed cycle. But how big can the dichromatic number of tournaments really be? Turns out arbitrarily large. There's a family of tournaments called Dn. It is known under many different names in the literature. It seems to be what the literature is starting to settle on. Is a recursively defined family of tournaments where the first member of this family is exactly a single vertex tournament. Then we can get the directed three cycle, so we need two colors. And then the third entry in this tournament is constructed in this cyclic manner, where we take two directed three cycles, make one of them out complete to the other, so we add all possible edges in one direction, and then we add one more vertex, and also make this out complete to the one directed triangle and incomplete from the other, with the idea being that we create a bunch of directed triangles. Now, why does this need three colors? Well, if we take any two coloring of the directed triangles, say that we consider this two coloring and maybe this two coloring. Now, whichever color we give the top vertex, it's going to be in some monochromatic triangle. So if we give it, for instance, blue, then we can find this directed triangle. And so it's not two dicolorable. In fact, it needs 3 dicolors. And 3 is always sufficient because the previous ones we can color with 2, and then this extra vertex we can give a private color. And this generalizes as to a sequence where every time we take these 2 members of the previous tournament in the sequence and then add these cyclic triangles with 1 extra vertex. And this is arbitrarily large chromatic number. Now this was first introduced in a very important paper in this area by Berger, Kormansky, Chudnovsky, Fox, Lubel, Scott, Seymour, and Thomasé. A lot of authors, and they really studied this in terms of its dichromatic number and showing that it has arbitrarily large dichromatic number, using that as a certificate for many other things. But what actually causes big dichromatic number? So here we see if you contain this tournament Dn. Yes?
Well, is there any estimate on the minimum number of vertices in the digraph of di-coloring number n?
There are some bounds, but they're not very good bounds. Because a lot of the people who work in this area currently come from the more induced subgraph land where people care less about exact bounds. So there's a lot of like tower of exponential bounds, but not like nice bounds on
the previous one is like 2 to the n, right? So
yes.
This is roughly 2 to the n.
Yes.
So is there any idea on how far this is from the optimal, or this is even conjecture that this would be optimal?
I don't know if anyone went as far as conjecturing that it's optimal, but I would be very surprised if you can do much smaller. The problem is that we don't know that many families that actually tend to infinity.
Should a random graph be a much better bound?
If you take a random graph with random orientation, it feels like it. I just don't know if you can kill a bunch of the cycles with fairly few colors. That's a good question, though. I don't think many people have studied anything random in this setting. It's very much about fixed orientation so far. That might be a more interesting question than the next 5 slides. But okay, so what causes big dichromatic number? There's some local certificates in the form of if it contains these subtournaments that we know have large dichromatic number, but there's no more general notion that's immediately obvious. Whereas for graphs, we at least have the clique number. Like if you have a large clique, then you contain then you need a lot of colors. And it's not immediately clear what the digraph equivalent is. Now, to get to an equivalent, we'll need a different representation of tournaments, which are called backedge graphs. And for a backedge graph, we first fix an ordering of the vertex set of the tournament. So here, v1, v2, v3, v4, in that order. And then we have a look at all the edges that go backwards. So here, drawn from right to left. So we call edges that go from left to right, we call them forward edges, and the ones going backwards, we call backwards edges. And now we can look at the undirected graph given by just the edges that went backwards. And if we fix the ordering of the tournament, this is exactly equal to the tournament. It's an equivalent representation because all the edges that are missing in this graph would go forwards in the tournament. So for any specific ordering, I get a backedge graph, but there are many possible orderings of a tournament, and so there's many different backedge graphs. So here the 2 tournaments on the left are the same tournament, just in a different ordering, and we get very different backedge graphs. The top one contains a triangle and is 3 colorable. This bottom one is disconnected. Very different graphs, and this is a problem in general. If we want to study backedge graphs, you have to consider all of them. However, it turns out that they do have a very nice property. Namely, the dichromatic number of a tournament is equal to the minimum over all chromatic numbers of its backedge graphs. So if you consider all the different possible orderings and all the corresponding backedge graphs, if you take the minimum over all the chromatic numbers of this backedge graph, that will give you the dichromatic number. Now, why is this? Well, if I have a coloring of the backedge graph, so for example this in the bottom, because a color class is stable or independent, it must be transitive. All the edges go forward. So it's also acyclic. So any coloring of a backedge graph is a valid coloring of the tournament in the die-coloring sense. And the other way, if we have a coloring of the tournament, then we can construct an ordering simply by taking first a transitive ordering of one color class of all the red vertices, and then we take a transitive ordering of all the green vertices, etc., for all the color classes. Then each of these color classes in this backedge graph corresponding to this ordering is stable because all the edges go forward. That's how we define this transitive ordering. And we don't care about the edges between different color classes because we just keep the same coloring. So these two are equal. And well, this is pretty nice because for coloring we do have a bound, namely the clique number. And this is exactly the notion of the die-clique number of a tournament. I say die-clique number. Die-clique number is generally what it's called for digraphs in general. For some reason, when we talk about tournaments, everyone just calls it the clique number. That's why the title of this talk. I'll try to use the die-clique number, but I might mess up sometimes and use clique number. Know that I always mean this notion of clique number. So it's a minimum over all clique numbers of the backedge graphs for the different orderings. And this was first studied by Aboulker, Aubian, Charbit, and Lopes. So then the next natural question is, well, do there exist tournaments of arbitrarily large die-clique number? It's not immediately obvious because at least for dichromatic number we have this nice notion of partitioning into acyclic sets, so we have some idea of how to work with it, whereas for die-clique number the only definition really is in terms of these backedge graphs, and checking all backedge graphs for a large tournament is quite annoying to do. But it turns out that we can use another result from this paper. Namely, they showed that the substitution closure of a Dicai-bounded class, where Dicai-bounded means that for this class of digraphs there exists some function f, such that for any graph in this class, the dichromatic number is bounded by this function of its die-clique number. If we take any Dicai-bounded class, and we take the substitution closure, so we exhaustively substitute digraphs in this class for vertices in digraphs to generate this entire class, then the resulting class is also Dicai-bounded. Now, why is this useful to us? Well, our class that we looked at previously, Dn, is built by substitution. Namely, we exhaustively substitute directed triangles into directed triangles. And so Dn, plus if you take the single vertex tournament, this entire family is contained in the substitution closure of the directed triangle and a single vertex tournament for D1. Well, a finite list of graphs is certainly Dicai-bounded. Just take like the function of the die-clique number of that tournament. And so as a result, the class of Dn is Dicai-bounded, but we know it has arbitrarily large dichromatic number. So it must have arbitrarily large die-clique number. Now it's not a nice relationship in the sense of Dn has die-clique number n, we have some logarithmic bounds, and we don't know whether that's tight, but at least we have a family that has arbitrarily large die-clique number, which seems sensible for a notion of clique number. Okay, so then we can ask, well, what causes large diclique number in tournaments? In graphs, we have this very nice notion that if you have large clique number, you contain a large clique. This sounds very rudimentary, but we currently don't have this for the diclique number. Because, well, we know that if you contain a large dn, you have reasonably large diclique number, but is this the only reason? Are there other constructions, or are there many other graphs that have large diclique number but don't contain a large dn? This was widely open. Nobody knew. Well, we thought for a while maybe dn is just the notion of a clique. It's this very simple, very nice construction. That turned out not to be true. There is another construction. So this is the construction that we call an. Again, in literature it's known by different names. And this construction is again recursive. We now start again with a single vertex tournament, and afterwards we define it here by its backedge graphs, because that's the easiest way to think about it, at least in my opinion. And what we do is we take a backedge graph where we first put a very big clique, and then between any pair of vertices of this clique in the backedge graph, so in this clique all the edges go backwards, we put a copy of the previous graph. And this was again first introduced to study diclique number. It was introduced by Ili and Ringi Kim. And so why does this have arbitrarily large dichromatic number? Well, if you have an n-1 coloring of this graph, dicoloring of this backedge graph, suppose that we have that, well then we have two vertices in this clique that receive the same color, just by pigeonhole. But then for any pair of vertices, we would have some copy of the previous iteration, so of an-1, living between them. And because this is a backedge graph, so there's no edges drawn between this, so all of those edges go forward. Well, by induction we may assume that this copy contains a blue vertex as well. Then this is a forward edge, this is a forward edge, and that is a backwards edge. So we get a directed triangle that's monochromatic, contradiction to it being a valid dicoloring. So also here we get that the dichromatic number of an is n. Now they additionally also showed that it's D3 free, so it even doesn't contain the third element of the sequence dn. And you can also show that the sequence an, or sequence dn, is A3 free. So from the third iteration, they really diverge. And so this shows that dn is not sufficient. If this has unbounded diclique number, which it does, by the same argument as dn, again it's a substitution-based construction. It's not quite the closure of a single graph this time, because every time we take a larger and larger and larger clique. However, what you can note is that what it is the substitution closure of is a tournament, the family of tournaments that look like this. A big clique and then single vertices in between. But this is two dicolorable. All the edges in the clique go backwards. So if you give that one color, that's acyclic. And all the vertices underneath that clique, all the edges between them go forward. So it's also an acyclic set. So we can also color it one color. So every element of this class is two dicolorable, so it's definitely two dichi bounded. And so again, by substitution, we get that the class an is dichi bounded, and because it has unbounded dichromatic number, it must have unbounded diclique number. Okay, so we now have these two families that have arbitrarily large diclique number. Is that it? Is there more? It's not obvious why these two should be the answer, but what we showed is that these are, in a way, the answer. Namely, for all n, there exists some constant such that if you forbid both AN and DN, your tournament has bounded diclique number. Now, the bound that we compute on this Cn is not amazing. We didn't try to optimize that constant very much, but we get a bound nonetheless. And so in a way what this says is that if you have large diclique number, it's really caused by having a reasonably large AN or a reasonably large DN. And so we also somewhat have a bounded size certificate of having large diclique number, even if the diclique number of the certificate is not equal necessarily to the diclique number of the tournament overall. Now, we also get a nice corollary, namely that if you have large diclique number, then there exists a vertex such that its out neighborhood has reasonably large diclique number. Why is this? Well, in either of these constructions, you can find such a vertex. So in Dn, if you take this vertex, its out neighborhood contains Dn minus 1, and so its out neighborhood has reasonably large diclique number, and the same in An. If you take this vertex, this An minus 1 is also contained in its neighborhood, so it also has reasonably large diclique number. And in fact, if you look a little bit more, you can find many such vertices in both these constructions. And this is known to be false for dichromatic number. In dichromatic number, this doesn't generally hold.
You mean in general digraph, right?
Yes.
Oh, no, no. But
Even in tournaments, I
tournaments,
actually. Okay. So, onto the proof. I will show you a bit of a high-level overview of the proof, and some of the elements we'll dive into a little bit more. But there are also some parts of the proof that are a little bit finicky and technical, so we won't do every detail of the proof. So actually, the first step of the proof is to prove this corollary. So it follows from our theorem, but to prove our theorem, we also need it. And we do this by showing the existence of big so-called mountains, which are a tool that was introduced earlier in the literature. Now, once we have that corollary, we use that to prove that if you forbid Dn, you can actually find bag chains. Another very standard tool in this area. Don't worry, I will explain later what it means. But it's some sort of nicely organized structure where you can really localize where the diclique number lives. And then we use a maximum bag chain argument to show that if you forbid both A and Dn, actually the rest of the tournament nicely attaches to this bag chain, and all of it has bounded diclique number. Okay, so let's start with mountains. They were introduced again in that original paper with many authors in the setting of dichromatic number. And it's another recursive construction, and it's actually very similar to some of the constructions that we've seen previously. So a one mountain is a single vertex tournament, and then we define that an arc is R heavy if there exists some R mountain that the head of this arc is out complete to and the tail is incomplete from. Why is this nice? Well, that means that if I have, the idea behind it is again doing induction on coloring, and if I need R colors to color an R mountain, then I know that these two vertices must receive different colors because otherwise they're in a cyclic triangle with a vertex from the R mountain. And then we define an R mountain to be a clique of R vertices such that any arc within this clique is R minus 1 heavy. And here I actually mean clique in the undirected sense. And we also, additionally in that R mountain, include all the certificates that these are R minus 1 heavy, so we include the R minus 1 mountains, showing that these edges are these arcs are R minus 1 heavy.
So what do you mean the certificates in here?
So the certificate for this arc, this is the certificate witnessing that it's heavy, and so we want to include all of those.
I see. So you might have more vertices because of the certificate,
Yes,
right?
you will have probably many more vertices. But one thing to observe is that I didn't say that each of these arcs has a private certificate. These certificates, these R-1 mountains might overlap. They might even overlap with the with this clique. So it's not a clean construction where there's exactly one object per iteration. There's many different possible R mountains.
So more of these R vertices, you want every pair to be joined by
Yes.
heavy R.
Yes. And we also do not care about the orientation of any of the arcs in here. We just care about that they're heavy. And this immediately then gives you the coloring result, what it was used for in the original paper, in that if every one of these arcs is heavy, each of these pair of vertices, the endpoints of every arc needs a different color. So in fact, when you look at the entire clique, each vertex needs a different color, and so you increase the clique number, or the coloring number, sorry, dichromatic number. Okay, so how do we use these? First, another example of a 3 mountain. So here I have a clique, and then for each certificate here, they're nicely disjoint. Again, in general, they need not be. So we're going to use this for diclique number, but that's a little bit more work. So first, to get there, I introduce a little claim. For every 2 coloring of an A plus B minus 1 mountain, it contains either a red A mountain or a blue B mountain. Why is this the case? Well, let's look at this clique such that any pair of vertices is joined by a heavy arc. And this clique is either going to have at least A red vertices or at least B blue vertices in any coloring. So suppose that there are at least B blue vertices. Well, then we look at an arc that connects 2 of these blue vertices. There exists some R-1 mountain that witnesses that this is heavy. And this is an A plus B minus 2 mountain, or an A plus B minus 1 mountain. So by induction, that contains either an A red mountain. If it does, great, we're done. We found our red A mountain, and we're happy. Or it contains a B minus 1 blue mountain. If it contains a B minus 1 blue mountain, that witnesses that this arc is B minus 1 heavy when looking at just blue vertices. But this is true for any pair of blue vertices. So in fact, we have a clique of B blue vertices, each pair of which is connected by B minus 1 blue heavy arc. And so we get a blue B mountain. So that proves the claim. How are we going to use this? Well, we want to show that R mountains actually have large diclique number, logarithmic. And to do that, we're going to consider an diclique ordering. What that means is an ordering such that the backedge graph has minimum clique number. So exactly the clique number of this backedge graph is the diclique number of the tournament. Now the first case is that all heavy edges of this R mountain in this clique, they go backwards. Well, if they're all backwards edges, it's an R clique in an R mountain. So we find a clique of size R in this backedge graph that is supposedly optimal. So our R mountain in that case has diclique number at least R. So we're done. Then the slightly harder case is not all the heavy edges go backwards, so at least one of them goes forward. Well, then let's look at what actually happens with that edge. With this arc, so there's some R-1 mountain that witnesses that this arc is heavy, and it lives somewhere in this ordering. Here I've drawn it with this purple outline. And what we're going to do is we're going to color all the vertices that come after this arc. We're going to color it blue, and everything that comes before we're going to color it red. Now this is a slight lie, of course. There might be some stuff in between. and then you color it depending on which endpoint it comes before and after. But in spirit, the argument is pretty similar to what it is here. And what we're then going to notice is, well, we definitely, by the previous claim, have either a red R/2 mountain or a blue R/2 mountain. And by induction, we then know that it has a clique, a red clique, or a blue clique in this ordering of size at least one less than what we want. Because we're looking for base 2 log of R. So we have at least one less, so we just need to grow this clique by 1. Well, suppose that we have a blue clique, and remember this is all backward edges. It might be bigger because it might not be the optimal ordering for that back edge.
Oh, sorry,
Yes.
I forgot about the color. So how did you choose red and blue?
So I choose all the blue blue colors that come after this edge and red before
In this ordering.
in this ordering. And this is this optimal diclic ordering. And there might be stuff in between, but that also works out. So we have some large clique in this blue part, but this part is out complete to this vertex. And so those are all backwards edges. And so we can extend this clique in this backedge graph. And this is an optimal ordering. So in fact, that we found a clique of size, of the desired size, means that this actually has the diclique number that we want. And the reason that I didn't specify the vertices that live in between here is because they can get either color and it works. So you just color them arbitrarily red or blue. Because if you find a red clique on this side, well, that is incomplete from this vertex, which are also all backwards edges. So if we find a clique of size log to our -1 here, then we can extend it with this one. And so in either case, whether we get a red R/2 mountain or a blue R/2 mountain, we always get a clique in this backedge graph of the desired size. And so showing that the diclique number is at least this lower bound. Okay. Now, we then want to use this to show our lemma, which we previously had as our corollary. I won't go into the details of this proof, but I want to share a couple of the ideas that help in this proof that work nicely. So we again proceed by induction on showing that tournaments with large diclic number but small diclic number for all of the vertices in their out neighborhood, this contains a mountain, a reasonably large mountain, and we induct on the size of this mountain together with the size of the diclic number. And we also may assume that there's actually a large minimum dominating set, because each vertex in its out neighborhood sees only a little bit of the diclic number of the tournament. So if we have a small dominating set, then the entire tournament has small diclic number. So we may assume that we have a large minimum dominating set, which is very useful for contradictions because we just find a smaller one. And also, if you have a mountain, because it's bounded size, you can just by recursion find upper bound on the size of these mountains. Their out neighborhoods have bounded diclic number. Just take the number of vertices and multiply this by the bound for the out neighborhood of the diclic number of the out neighborhood of a single vertex. So in fact, what we can do is if we have a mountain, we can delete its out neighborhood and still have large diclic number in the remainder of the tournament, allowing us to build these structures, build larger mountains, or get a contradiction with DM.
Sorry,
Yes.
I'm a bit confused. Are 2 and 3 some tools you use to prove 1?
No, we use 2 and yes, we use 2 and
Okay,
3 to prove
Because
one.
if you prove one, you are done, essentially.
Yes, if you
right?
prove
Okay.
1, you're done. 1 is the general proof strategy. 2 and 3 are like observations that we
Okay,
use to prove 1.
thank you.
Good question. Okay, so that is a very hand-wavy idea behind the proof of the corollary. So now we're going to use this to show that we have backchains. So what are these backchains? They were introduced by Harut-Yunyan, Lei, Newman, and Thomasé, again for dichromatic number, and they're the structure where we have these sets called bags, and a bag has exactly a specified dichromatic number. So exactly dichromatic number, C, not one more, not one less. And additionally, between adjacent bags, there is some further constraints, namely a vertex, if you look at its wrong direction neighbors, where with wrong direction neighbor, I mean a neighbor that if you would order this as your backedge graph in this ordering, they will be backwards edges. We consider those wrong direction neighbors, so neighbors to the left. If you look at the out neighborhood of a vertex in the previous bag that are wrong direction neighbors because they're in the previous bag, then their dichromatic number is small. It's very small. This A can be much, much smaller than C. And also wrong direction neighbors to the next bag. So if you have a V or its in neighbors in the next bag also have small dichromatic number. And this is a standard structure that you can use to show many nice properties, and it's one of the most successful tools in the area.
Is it only the previous and next bag, not the ones beyond?
It's only the previous and the next, but in every proof that involves these backchains, the next step is to show that it actually holds for everything. So very good question. In fact, when we go to our setting, where we just do exactly the same, except we replace dichromatic number as a measure of size by clique number, because our base case already gives us that, in fact, this relation holds between bags arbitrarily far apart, we just include that in our definition. So for us, when using the clique number, it doesn't just hold for adjacent bags, but if you look at bag 2 and bag 1000, wrong direction neighbors of a vertex in bag 2 in bag 1000 still have small clique number. And otherwise, we just use exactly the same notions, just clique number instead of dichromatic number. It makes some things a little harder to prove, but generally our proof is still going to be very similar in structure to those used for dichromatic number, if you've seen these before. Okay, so the first thing that we're going to do to show that we actually contain such backchains is that we're going to take this claim that if you, or this lemma that we have, that if you have a vertex, if you have large clique number, that you have a vertex which out neighborhood has reasonably large clique number, to actually under the same setting, if you blow up the have an even higher bound for your clique number, then there exists some vertex that not only has the large clique number in its out neighborhood, but also in its in neighborhood simultaneously. Note that by just reversing all arcs in our tournament, this result also holds for in neighborhood. However, they don't hold simultaneously out and in neighborhood. We do actually need to prove that. So how are we going to do that? Well, suppose that you have some tournament with huge clique number, and now I'm going to select two sets. The blue set is going to be the set of all vertices from whom the clique number of its out neighborhood is small, and the red set is the set of vertices from whom the in neighborhood, the clique number, is small. Both these sets can overlap, but I claim that each of these sets actually has small clique number. Why is that? Well, if it has large clique number, we use our claim to get a vertex in that set of large clique number in its out neighborhood. Well, then it certainly has large clique number in the entire tournament. So we then immediately obtain a contradiction, and so we know that both these sets have small clique number, but then because we start with a set with huge clique number, certainly there's something here still of big clique number. And in fact, what this shows is that as long as you make this bound for the clique number big enough, we don't just get a vertex that has both large diclic number in its out neighborhood and in its in neighborhood, but we can get arbitrarily many. We can get many, many vertices with large neighborhoods where diclic number is the measure here of size, both in neighborhood and out neighborhood. And this is again very useful when we start making our bag chain, because well, we can delete a lot of stuff and still have large diclic number in our out neighborhood and in our in neighborhood. And if you have something large, then we are going to apply induction on diclic number to get nice substructures. Saying all that, I'm not going to show you the exact proof of how we actually get the bag chain because it's a bit tedious. But what we can prove is that you get a bag chain of length 2, where the length is the number of bags. So we get 2 bags with the desired relation between them. Now for our proof, having just a bag chain of length 2 is not sufficient. So we need to get a bigger bag chain, but we're only able to prove 2. Well, these bags have some specific large diclic number. What if we make that really, really large, so we can just find smaller bag chains within them? If a set has large enough diclic number, it contains a bag chain of size 2, that's something we showed. Well, we're just going to find a bag chain of very large diclic number, so we can recursively find a smaller bag chain within that. And once we have that, for any vertex in one of these bags, its wrong direction neighbors within one of these bags are a whole, because it's a bag chain that we found there, and then between two such sets, so between B2 prime and B3 prime, it holds because they're embedded in this original bag chain where we already had this condition. And of course we drop the clique number, or the diclic number of this bag chain that we get quite a bit, but that's okay. We can blow up all our numbers to be really big and then it still works, and we can get still as large as we want. And we can repeat this process to get bag chains of whatever length we desire. For our argument, we just need bag chains of length 8, so we just apply this operation twice, but you can do it arbitrarily many times, as long as it's a fixed number of times. Okay, so now we have a bag chain. What are we going to do with the bag chain? Well, we're going to take a maximum bag chain and show that the rest of the tournament attaches somewhat nicely to it. And for that, we introduce this notion of zones. This was also already used in a dichromatic sense. We here used in the diclic sense with slightly different indices, but overall it's the same idea, where we try to fit things in the bag chain. And we put a vertex V, like this one, we put it in this zone 1.5 if bag 2 is the highest index bag, such that it has a lot of wrong direction neighbors here, where a lot is in the diclic number sense. So everything after, so B3, B4, B5, all the way up to the end, it actually satisfies the idea of being in this bag chain in the sense of it had its wrong direction neighbors in this set have small diclic number. Any vertex that we can't nicely assign because it has big diclic number wrong direction neighbors in every set also go in this set Z1/2. Now what we want to show is that this sort of attaches nicely, more nicely than just by this definition, and that also the relation between these sets are nice. And these arguments are almost every step the same. I'm going to show you the steps. I'm not going to show you the arguments for the steps because it's almost always spot the DN. Find some way of constructing DN by deleting certain sets until you grow your DN. And also these steps are the same as for any bag chain argument. Just sometimes the precise argument is a little different of how to achieve it. So the first thing we show is that we had this condition within the bag chain that any vertex has, when you go look at any other bag, its wrong direction neighbor have small diclic number, and we actually show the first step is that even if you take a union of bags, its wrong direction neighbor in that set still have small diclic number. Then the next step is showing that zones behave nicely with respect to the bags. So for any vertex in the zones, if you look at the bags that are sufficiently far away, where sufficiently far is like 3 steps over, then their wrong direction neighbors have small diclinic number. Again, you find a dn somewhere. Then we do the opposite as well. So for any bag, we show they behave nicely with respect to zones. So any bag, far enough away zones, they have small enough wrong direction neighbor diclinic number. This picture is getting messy, I know. But this actually allows us to say something interesting, because this means that the zones really almost fit into this bag chain. They don't quite work nicely with the sets that are quite right next to each other. And we don't know what its dichromatic number is. But if we throw out, say, a couple bags here and we substitute this in, if it had the right dichromatic number, it would work. So in fact, we know that each of these zones has bounded dichromatic number. Because if it has arbitrarily large dichromatic number, then we can find a large bag chain with exactly the size, the right value for C, so for the dichromatic number of each of the bags. We can delete a couple of these bags and slot this in. But that contradicts the maximality of our original bag chain. So in fact, each of these zones has bounded diclinic number. Okay. Now, the final thing that we need to show here is that then the zones also behave nicely to one another. Again, you find dn, otherwise, and we get that also between zones, if they're sufficiently far apart, they have small wrong direction neighbors in the diclinic number sense. Now this is all nice and good, but why do we care that these zones attach nicely and have nice relationships between them? Well, we can partition the entire tournament then into 4 what we call near bag chains. So we have the original bag chain, which is just a proper bag chain, and then to choose things far enough away, we partition the zones into 3 sets, taking all the zones with indices mod a half, or half mod 3, 1.5 mod 3, 2.5 mod 3. And these are what we'd like to call near bag chains. They are bag chains X with the relation between them, but the dichromatic number of each set is not exactly what we want. They're not constant. We have some upper bound for them. Additionally, what we can do is merge, within such a near bag chain, we can merge bags that are adjacent and of small diclinic number to get a lower bound for them as well, so we have some sort of range that their diclinic number is in, but we don't exactly know. It turns out, however, that this is enough, because finally we can show that these near bag chains, if they're A and dn free, have bounded diclinic number, and we have 4 such near bag chains. So if we can show that, then we're done. So how do we do that? Well, each of these sets has bounded diclinic number. So if the whole picture has big diclinic number, then the large diclinic number must come from somewhere. So if you take this ordering to be a backedge graph, where we take small diclinic orderings for each of these individual bags, then there must exist a big clique between the bags. Now once we have that, we can clean up in the sense of, well, for each of these vertices of this clique that we want to keep, we delete all the wrong direction neighbors in all of the bags, which is valid because those are little sets when it comes to diclinic number, so we can delete them. And then the rest will still have large diclinic number, so by induction we can find an minus 1. And we can find that in all the places where we need to find it. And there you have an, a contradiction. Interestingly enough, this is the only spot in the entire proof where we need an. Everything I've said before this picture, before this slide, holds with just forbidding dn. It's only when you get to this part that we also need an. And this is also why for a long time we thought that dn was just a full answer, because we could get quite far into the proof. But we kept being stuck until we realized that there's the second tournament that also needs to be forbidden. And that then completes the proof. So we first showed that you have this vertex of out neighborhood with large diclique number, and also the same for in neighborhood. We then use that to find bag chains. That part I definitely didn't go into much detail. And finally we can use that to then do a mostly standard backchain argument to show that in fact the entire tournament must have bounded diclique number. And that then shows the main result that for any integer there exists some constant such that if you forbid both an and dn, a tournament that doesn't contain either of them has bounded diclique number. Now this is for tournaments. We don't know for digraphs. That's an open question. But otherwise this provides essentially a complete answer. So if you're looking for, say, forbidding a bunch of induced subgraphs and subtournaments and wanting bounded diclique number, then it's suffices to forbid an induced subgraph of both some an and some dm. And similarly also actually for if you look at dicai bounded classes, this shows that essentially you only have to care about classes where it's also the diclique number is bounded. And there's some fun implications there, but really what we cared about and what we set out to show is that we now have some sort of canonical object for dicliques in tournaments. And they're fairly nicely structured. But is this a full answer? No, I can still not tell you if a tournament has diclique number n, why it's exactly n. I can just tell you, well, there's some dn or an of size at least log, very small. Some tower of exponentials was involved in this proof. I'd like to end there. Thank you.
Thank you. Any questions? Yes, Richard?
Yeah, so I wonder, like, if say we have a random tournament, then what would be the parameters be like? Are there anything known on that?
I don't think it has been studied.
Because I just remember that people from the probabilistic side, they care a lot about the chromatic number of a random graph. So I wonder whether this would be something interesting to think about.
Yes. No, it's definitely an interesting question. I think just the people who have been involved in studying dichromatic number and definitely diclique number have been from the more structural side and the less probabilistic side.
Maybe you can work with him this week.
There's definitely a lot of open questions there with possibly very interesting results, for sure.
Yeah.
So do you think this would also be the only two obstructions for digraphs, or do you think there would be more?
Ooh, that's a good question. So if it were to be the only obstruction, that would give an interesting notion of that diclique number is sort of dominated by this diclique number of subtournaments, which seems quite strong. Because if these are the only two obstructions, then look at your biggest subtournament, and that must then contain a large dn or an. So then your subtournaments would have large diclique number. And I'm not sure I believe that, but I also definitely don't have a counterexample. So.
So, I have two questions. The first one is, do you know any construction of tournaments of large dichromatic number that excludes both an and dn? Because at least, yeah, right. because they bound the dichromatic number,
Right.
but dichromatic number is upper bound of dichromatic numbers. So
Yes. I'm thinking about the heroes paper because DN is a hero, so
well, I don't think DN is hero because in the construction of hero, one part has to be transitive.
right. Okay. Yes. You're right. So it's not a hero. So this is also just generally, I think, a problem that, I mean, you've definitely encountered too, where there's only like 3 or 4 known constructions
Yeah,
in general of large dichromatic number graphs, up to some randomness. There might be some way of constructing mountains if you choose your cliques, the orientation of your cliques cleverly, but I'm not entirely sure if that's possible.
And my second question is, so if you exclude a hero,
Mhm.
then it has bounded dichromatic number, so it has bounded dichromatic number.
Yes.
And if, for example, if you exclude a really simple hero, then can you compute the optimal ordering of the clique number,
The optimal ordering.
or the approximation version might be fine.
I mean,
For dichromatic number or clique number?
Dichromatic number.
for the diclic number.
Yeah.
So you have some upper bound on the diclic number.
Yeah. So someone promised you that it has somehow bounded dichromatic number.
Mm-hmm.
So I'm thinking of the promised version.
Mm-hmm.
So, and you want to really find an ordering that is, whose width is close to the optimal width.
I mean, if you have an actual bound,
Or just use exclusive subtournament, then can you find
I can, like, if you give me some actual bound, then sure, I can find you an approximation. Sorry, if you give me the, which way to go the implications is always a good question.
for example, if for dichromatic number,
Mhm.
even if someone promised you that
Yes.
it is two dicolorable, I think it is a bit hard
Yes,
to
I believe
find
this
two dicolorable.
same is true for diclic numbers still. There's some people looking at the complexity. I don't know if their work has been published yet for diclic number.
But I think they were just showing that without any assumptions, deciding if dichromatic number is the most K is hard.
Now, approximation, I think, might be possible, in the sense of we know you won't be able to get anywhere exact, but at least for approximation, we know some bounds on the diclic number given what AN or DN it contains. But I like any sort of good approximation of an actual ordering, I don't know if you can do that. I would be surprised if you would be able to do that efficiently.
I have questions. You said that for tournaments, when the diclic number is large, you have vertices that out neighbors have large
Mhm.
diclic number.
Yes.
So that's not true for dichromatic number.
Yes.
Is it an easy example where it's not true? Or
No, it's a long proof
I
from the literature.
What if I define a fractional diclic number?
Ooh.
Then like taking fractional clique number or
Mhm.
fractional chromatic number equal,
Mhm.
right?
Yes.
So it's in between. Then is it true or false?
That's a good question.
Yeah.
So then whether you have an out neighbor
Yeah.
of high fractional dichromatic or diclic number. I'm not sure.
I think that is recently proved by Ungers and Seymour.
Oh.
And
Has it?
even the 2x bound, is
For the dichromatic number.
Fractional version.
Okay.
Let's see. He's coming, so.
Yeah.
Right. Any other questions? Yeah.
I was wondering if you're trying to, let's say you're trying to prove chi-boundedness with this notion.
Mm-hmm.
So, okay, if I'm trying to do chi-boundedness in graphs, there's probably going to be at some point in the proof, oh, look at this subset of vertices.
Mm-hmm.
It has it's covered by some neighbors, so the clique number is smaller, so you can color it by induction and blah, blah, blah. Do you have some idea of what could be the equivalent of this kind of argument for these notions?
So, almost any argument, any sort of coloring argument with die coloring seems to be of the form, I have an edge, it's directed one specific way, and then in the intersection of the out neighborhood of the head and the in neighborhood of the tail, I have some large dichromatic number substructure. Other than that, for Dicai boundedness, there's very little known for Dicai boundedness. Other like substitution is known, but like specific results for even graph classes or orientations of graph classes is very sparse in literature. This is a problem in general in this area. There are very few tools. I've shown you essentially all the tools that are common in this area, and it's mountains and backchains for anything like remotely hard.
Okay, any other questions? If not, let's thank the speaker.